Hey, here's a short screencast on the topic of method of exhaustion. The method of exhaustion, this is a classical name for a process. So that's one of the reasons that I'm using it, to expose you to an important term in the history of mathematics and science. But let me establish for you the context in which this occurs. I've been talking about this idea where we have a continuous positive function on an interval from A to B. And we want to solve the area problem for this. That is, we want to calculate the area of this region, the area under the graph. Or area under the curve, as it is so often said in calculus classes. I've said in a previous screencast that the method we use has 3 steps, and I'll just paraphrase here. The first step is we approximate with rectangles by cutting up our region and adding up the areas of the rectangles that approximate. And I have done a screencast on this previous to this. The second step in our method is using this method of exhaustion. So we take this work and we bring it to another level using this method of exhaustion. And we look at the sum of areas of rectangles, and take the limit as the number of rectangles goes to infinity. That is, it increases without bound. Now, this is what I want to talk about today. The reason that we do this is because what we get is the exact area of this region. So the method of exhaustion is a crucial point or a crucial step in solving the area problem, finding the area under a curve. So let me describe what the method of exhaustion is. If you start approximating the area with some rectangles, the typical way of doing that is saying, well, if we let AN be the area, or the total area of rectangles of n rectangles used to approximate the area of the region. So let AN be the area you get when you use n rectangles. But what we've talked about to this point is we've talked about how would you calculate A of 5? How do you calculate the area using 5 rectangles? Well, step 1 of our method is you divide the interval into 5 subintervals of equal length. That gives you a slicing of our region. And then we've been using the right endpoint to calculate the heights of our rectangles. And so that's what the rectangles would look like, 5 rectangles. And we sum the area of those rectangles. So in our case, A5 is the sum, as I goes from 1 to 5, of f of xi delta x, right? That's the generic form. Our function, we've just got a generic function, f of x, but we could do a little bit better with the i's, or the xi's. Xi is the left endpoint plus I times delta x. And I guess we could do a little bit better with our delta x too. Our delta x is the length of our interval b minus a divided by 5. So we get a formula that looks something like this that would give us an area of 5 approximating rectangles. To do the method of exhaustion, we don't want to use a concrete value for n here. We want to just work directly with this formulation for a sub n, or a of n. So let's take a look at what that would look like. So a of n, the area we get using n rectangles, looks very similar. Now, in fact, here's the generic way to write that down. But unlike the case where we had 5 rectangles, our delta x is going to look like this. We had a 5 before, but now we're just going to put an n. And our xi is going to look like this. Before we had a 5. Using those, our an will look like f of a plus I times b minus a over n times b minus a over n. Slight difference, but it makes a difference because we want the n to be inside our expression here, along with our index I. Then here's what the method of exhaustion is. The method of exhaustion says, let the number of rectangles increase without bound. And then the area of the region is going to equal the limit as n goes to infinity of those areas. Specifically, the area of the region is going to be exactly equal to the limit as n goes to infinity of the sum as I goes from 1 to n of f of a plus I times b minus a over n times b minus a over n. So the method of exhaustion is taking this limit. The method of exhaustion is giving us this thing right here. And what I need you to know about this, right, this is pretty intimidating looking. But you know exactly what every piece means. You know what this delta x is. You know that this in here is just the xi. You know that this summation right here is just an approximating area. So don't be intimidated by this complex looking expression. You know what it means. It doesn't change the fact that it's complex. But that's also a complexity that you can deal with knowing what you know about the way algebra works. So, intimidating looking, but really important. Because this thing right here is what we call a definite integral. And because it's got a lot of stuff going on, mathematicians have made a shorthand notation for this, and we write this as a shorthand. We appropriate the notation for the indefinite integral, and we add these things called limits of integration. So the rest of our course is basically going to be about understanding this stuff and working with these definite integrals. You need to know that this means this, where this limit here is the method of exhaustion. Soon I'll show you the fundamental theorem of calculus, which gives us a different way to calculate this value, that will actually bring in the differential calculus. But for now, this is a definite integral. It's very important to us, and it represents the area under a curve. In the case where the function here is positive and continuous. There's other ways to interpret it, but this is a really good way to start developing intuition for what this number means. So I'll leave this here now. This introduces you to the definite integral and the method of exhaustion, and in subsequent screencasts I'll show you how to work with that. See you then.